26th May 2025 from 7 to 8 p.m. See you there. Let's build a low carbon future together. Pre-Symposium Webinar Series Episode 5 International Symposium on Agriculture and Environment 2025. As we explore the powerful potential of low-carbon geopolymer concrete made from industrial waste, presented by the visionary Professor Martin Anda from the Harry Butler Institute, Murdoch University, Australia. Don't miss this chance to learn from a global expert and spark your thinking on sustainable construction. 26th May 2025 from 7 to 8 p.m. See you there. Let's build a low-carbon future together. Pre-Symposium Webinar Series Episode 5 International Symposium on Agriculture and Environment 2025. As we explore the powerful potential of low-carbon geopolymer concrete made from industrial waste, presented by the visionary Professor Martin Anda from the Harry Butler Institute, Murdoch University, Australia. Don't miss this chance to learn from a global expert and spark your thinking on sustainable construction. 26th May 2025 from 7 to 8 p.m. See you there. Let's build a low-carbon future together. Pre-Symposium Webinar Series Episode 5 International Symposium on Agriculture and Environment 2025. As we explore the powerful potential of low-carbon geopolymer concrete made from industrial waste, presented by the visionary Professor Martin Anda from the Harry Butler Institute, Murdoch University, Australia. Don't miss this chance to learn from a global expert and spark your thinking on sustainable construction. 26th May 2025 from 7 to 8 p.m. See you there. Let's build a low-carbon future together. Pre-Symposium Webinar Series Episode 5 International Symposium on Agriculture and Environment 2025. As we explore the powerful potential of low-carbon geopolymer concrete made from industrial waste, presented by the visionary Professor Martin Anda from the Harry Butler Institute, Murdoch University, Australia. Don't miss this chance to learn from a global expert and spark your thinking on sustainable construction. 26th May 2025 from 7 to 8 p.m. See you there. Let's build a low-carbon future together. Pre-Symposium Webinar Series Episode 5 International Symposium on Agriculture and Environment 2025. As we explore the powerful potential of low-carbon geopolymer concrete made from industrial waste, presented by the visionary Professor Martin Anda from the Harry Butler Institute, Murdoch University, Australia. Don't miss this chance to learn from a global expert and spark your thinking on sustainable construction. 26th May 2025 from 7 to 8 p.m. See you there. Let's build a low-carbon future together. Pre-Symposium Webinar Series Episode 5 International Symposium on Agriculture and Environment 2025. As we explore the powerful potential of low-carbon geopolymer concrete made from industrial waste, presented by the visionary Professor Martin Anda from the Harry Butler Institute, Murdoch University, Australia. Don't miss this chance to learn from a global expert and spark your thinking on sustainable construction. 26th May 2025 from 7 to 8 p.m. See you there. Let's build a low-carbon future together.
Hello, good evening, everyone. It's my absolute pleasure to welcome you to all to the Pre-Symposium webinar series organized as part of the International Symposium on Agriculture and Environment, ISAE 2025. ISAE 2025, hosted by the Faculty of Agriculture, University of Ruhuna, Sri Lanka, is set to take place on 2nd September of this year at the Goldface Hotel, Colombo. This year, we are excited to focus on the theme, driving innovations in agricultural technologies for climate action and sustainability. For more details, please visit our website. Now, let me extend a warm welcome to our distinguished speaker today, Professor Martin Anda, who will be sharing his insight today on industrial waste to low carbon geopolymer concrete. Professor Martin, we are honored to have you with us today. And I would like to warmly welcome Mrs. Chinta Rupasinghe, our moderator for today's session. Ms. Chinta Rupasinghe is a renowned academic and experienced organizer of international events like ISAE. She is currently serves as a senior lecturer attached to the Department of Agriculture, Engineering and Environmental Technology, Faculty of Agriculture, University of Ruhuna. And Ms. Chinta was also the past coordinator of ISAE 2018. Thank you very much for all of our local and international participants who have joined today. We truly appreciate your presence and hope this session will be both insightful and engaging. Now, let me invite Ms. Chinta Rupasinghe to take over as the moderator. Over to you, madam.
Thank you very much, Dr. Dushant, and good evening, you all. Actually, it's my great pleasure to introduce today our keynote speech on Pre-Symposium webinar on ISE 2025. I want to introduce Professor Martin Anda. He's an environmental engineer with over 30 years experience in the energy, water, and construction sector. Since completing a Bachelor of Engineering in Mechanical degree at the University of Western Australia, after working with consulting engineering firms on large industrial energy projects, he spent 15 years working with remote indigenous communities across Australia and developing countries, and completed a PhD during this time. Actually, as a country, we know that we also want to have many sustainable solutions to our energy, and also it's a kind of issues we want to manage our waste product, right? As agriculture country, there are many waste we develop. And later he joined Murdoch University and became a research manager, then director of the UNEP Environmental Technology Center. Later, chairing the Environmental Engineering undergraduate program. Professor Martin is team leader, circular economy in the university's Harry Butler Institute, where he manages postgraduate research on industry-focused research projects. He conducts a range of renewable energy, water, and waste-related projects and teaching across Australia and Indonesia. I think it's a high time to get the service of the Professor Martin for our Sri Lanka also. His current project include development of Australia's first indigenous on renewable hydrogen logistic company in the Pilbara, development of the first commercialized low carbon geopolymer concrete products. And he's a renowned scientist with he produced about 33 articles published recently. Altogether many articles, but from 2019 he published the Q1 journals about 33 articles. He has a high H index and also I-10 index. And he was chairing many conferences and their committees and also their sessions. And he even delivered a TED talk on climate change. He delivered about how should we live in this the current scenarios, right? And he delivered many keynote speeches in many events. Right now, Professor Martin, it's the time for you. Then the floor is yours for start to deliver today's speech. Thank you very much.
Thank you, Mrs. Chinta, and it's a great pleasure and honor to be here. I was very lucky to visit Sri Lanka in January and also visit your wonderful University of Ruhuna. So now it's a good opportunity to share my talk with you. Would you like me to share my slides from here? I should share my screen with you, Mrs. Chinta? Or you would like to show the slides from your side? What's the best?
You can share, Prof. Martin.
Okay. All right, let me have a look. Let me share my screen. Okay. Okay. Okay, how is that? Can you see my screen?
Yes, now we can see the screen. Yes,
Very
we can
good.
see your screen now.
Very good. Okay, so today, everyone, Mrs. Chinta asked me to speak on industrial wastes to low carbon geopolymer concrete. So I will largely speak from the perspective of my work here in Australia, but as I mentioned, I was very lucky to be able to visit Sri Lanka in January for the first time and actually meet
Excuse me,
Mrs.
Professor Martin. Excuse me,
Yes,
sorry for disturb you.
yes.
Can you move to a PowerPoint presentation mode?
Okay.
Yes, please.
It's not in that already? You
Still,
mean like full screen mode?
right, yeah, right. Now,
Yeah.
yes, yes.
Okay,
That's very
there we are.
fine. Thank you very much.
Very good. There we are. Okay. So, but luckily, because I was able to visit Sri Lanka in January, I was also able to meet Mrs. Chinta and other colleagues at the University of Rahuna and come to understand that they have a great interest in this area of low carbon construction materials, particularly when derived from agricultural residues and waste. So I realised then that it was going to be a great opportunity for us to work together and collaborate. So let me give this presentation today with a focus largely from the perspective of Australia, what we're doing there, but also some few insights into what may be possible in Sri Lanka if we were able to work together in this space of low carbon construction materials from industrial waste, particularly for geopolymer concrete. In Australia, we always like to start with an acknowledgement of the country on which we are speaking. And normally, of course, this is from my position at Murdoch University, where we have the traditional lands of the Whadjuk Noongar people. They're the traditional owners, the Indigenous people, First Nations people of the land at Murdoch University, and we pay our respects to their elders, past and present. And in fact, the country on which Murdoch University sits has been a place of learning for many thousands of years. So let me give a brief introduction to this topic today. When we think about the agriculture, mining and mineral reprocessing industries, we know that these are vital for economic development. We also know that they generate significant amounts of waste materials, and this can lead to various environmental impacts. So the question is, how could we go about reducing this waste material, because it's still a significant challenge? And one of the key solutions that we're talking about today is recycling these wastes into new materials. And the result of that could be the end of waste for these mining and agricultural operations. And we can consider them then to be byproducts or co-products. And this may indeed also be a transition to a circular economy. In Australia particularly, we have a lot of tailing storage facilities. These are the mineral residues that are disposed of in the tailings dams. I guess there may be some in Sri Lanka as well, even though there's not a big mining industry there. For example, in the coal-fired power station in the north of the country, I haven't visited there, but I guess there may be some storage of the fly ash after the coal is burnt, and that may be in large storage dams, but I guess I need to look into that further. A lot of that fly ash I know is already used in the concrete industries as a supplementary cementitious material. Now, the improper management of these tailings can lead to environmental degradation, and can harm human ecosystems. Likewise, the agricultural biomass residues, for example, what we may see in Sri Lanka is the rice husk ash from when this is burnt in the fields or in the boilers for other processing operations. Now, these wastes are rich in aluminosilicates, and we can actually use these as precursors to make a low carbon concrete that we may call a geopolymer or an alkali activated material. So if we look at transforming these industrial and agricultural waste into low carbon concrete, a geopolymer concrete, we know the background here is that cement is the world's single largest source of carbon emissions, as you can see in the pie chart here, at around 8% of global emissions. And the reprocessing of these industrial and agricultural residues can produce this low carbon concrete, for example, geopolymer or alkali activated cement. And this could be a significant step towards sustainable construction and resource efficiency. Now, where I'm based in the state of Western Australia, we now know through some work that we've started by my research team, and in particular, the present paper is being written by one of our research students. Her name is Amitha Varghese, and in the work that she started, she identified from various environmental approvals that there are some 1,000 tailing storage facilities in various stages of operation. They're either active or proposed, or they're operating, or they're actually closed already. Some of them, of course, are very old. They might be 100 years old from old gold mining operations, for example. And in her work, she was also able to establish that probably 50 of these do have the aluminosilicates that we're looking for to convert them into the as a precursor for geopolymer concrete. Now, by using these tailings and the aluminosilicates in them, where they occur, this geopolymer concrete offers a number of benefits, actually, and opportunities, I should say, as well. It facilitates sustainable construction, reduces waste generation, promotes local resource utilisation, and enables greenhouse gas emissions reduction. And as mentioned, this aligns with those principles of circular economy. So we have a big opportunity in Western Australia because it has such a large mining industry, and historically the tailings have not been managed well. And so it's now an opportunity. And so the work that Amitha will do is to try to identify the tailings with the best chance of being used in an economically viable manner. In other words, they may be near a regional centre where there is a market for concrete products, so the distance to extract and transport those materials may not be too far. So she's setting up a database in which she can then tabulate all of that relevant data, and that from there, investors, for example, could make a decision as to whether to develop that resource into a new concrete industry. Okay. So geopolymer concrete, what is it then? This is a alternative cementitious material to ordinary Portland cement, which is commonly used to make concrete at about 10% of the total volume of the concrete, along with sand, aggregate, small stones, and water. But geopolymer cement is quite different in that it requires no heat or limestone in its manufacture, and does not release CO2 in a way that you might know from the manufacture of ordinary Portland cement, which is made in very large kilns, where coal is typically burnt to do that in large rotary kilns. And of course, Sri Lanka does manufacture cement, and there is a kiln, I believe, in the north, and Sri Lanka also imports clinker. And I was lucky enough to go with colleagues from University of Ruhuna to a cement factory in Galle while I was there in January. So that was great to visit that and see the large scale of cement production there. But of course, this is the high carbon footprint material. And in fact, we can actually make the geopolymer cement from 100% waste-derived materials. And if we compare geopolymer cement to ordinary Portland concrete, we find that it can actually have, in some situations, better strength and better bond performance. And it may actually be better suited in some applications, such as marine infrastructure, because of its chloride resistance compared to ordinary Portland cement concrete. And I just put a couple of photos there in this slide. One of our earlier research team members, Jared Allery, you can see him there in our lab where we're testing different samples of geopolymer concrete that he's made. In the bottom photo there, you can see him holding a concrete cylinder. That is the 1.5 litre cylinder that we cast to put that in the compressive strength machine to see what compressive strength we've got out of that sample. And then also in the top right photograph, he's there doing the slump test on the concrete just to see if we've got the right workability for it. Now, it's quite substantially different, actually, a geopolymer compared to a concrete or cement that's being made with ordinary Portland cement. The Portland cement on the left there is essentially a hydration chemistry, and the geopolymer is a polymerization chemistry. And if you want to learn more about the very complex chemistry behind these two different systems, you can actually download this paper here by Professor Davidovits in France. He's the world leader, really. Professor Davidovits has probably been working on this since the 1970s. But I did read once, actually, that it was a Ukrainian professor in the 1950s that first started this scientific work on geopolymers. So the history is quite interesting, in fact. Now, if we look at the properties of geopolymer concrete, we find that it could, if prepared effectively, it can achieve superior strength and bonding compared to ordinary Portland cement. It can have superior mechanical properties in flexural strength, compressive strength, modulus of elasticity, and durability. And it can actually achieve chemical resistance as well, ensuring its durability in construction projects. And interestingly, one application where geopolymer is used, in addition to marine infrastructure projects, is actually in sewer pipes. In large sewer pipes, geopolymer can resist attack from various gases and chemicals that may occur in the sewage, traveling long distances in sewer pipes. And so there is actually a company in Melbourne, Rockler, that does actually manufacture on order sewer pipes from geopolymer. So you can actually see some particular applications there because of these benefits. Now, what I've done is prepared a diagram here, you can see there, that shows the different phases that we go through in the manufacture of a geopolymer concrete. 5 phases: the feedstock materials, the characterization, the mix design, the geopolymerization, and the products. And if we start with phase 1, you can see there that we want to collect the waste materials. It could be from these tailings storage facilities. It could be from the rice husk ash and the boiler ash around Sri Lanka, or the fly ash dams. And what I've been looking at is these collection areas. We could call them circularity hubs, and we may bring together a range of different materials that we can use as both the precursors to make the geopolymer concrete, or to be used as aggregates in the concrete itself. And so we may need some pre-treatment here, milling of the fly ash, for example, or screening of the aggregates if, for example, it's construction and demolition waste or coarse mine tailings. In phase 2, we need to characterize these waste materials, and there's a whole raft of tests that we would do to determine the reactivity of the material. In other words, we're particularly looking for how much of the aluminosilicates in these industrial wastes are in the amorphous phase, and then we can determine a mix design from that. In other words, what type of activated chemicals we need to add. But if these wastes are going to be the aggregates, well, then we might need to do a range of testing and on them, such as particle size distribution and compressive strength and so on. Once we've done that, we can go into phase 3, which is developing the mix design, and the chemistry behind that can get quite complex. And from that, we can determine which ratios of activated chemicals, what proportions we need. Most commonly, this is sodium silicate and sodium hydroxide, and the ratios are calculated to arrive at the mix design. And then these are put in the reactor to achieve the right mix of these activated chemicals. And then along with the precursor material, we go into phase 4, which is the geopolymerization, where we want to prepare the binder from the precursor and the activated chemicals. And then we go into the concrete batching plant with the aggregates. And there may need to be a small amount of water added just to get the ratios right and the workability right, but not in the same way that you add water to a normal concrete batching plant. You have to be very careful, in fact, that you don't add too much water, and that's a small amount usually in the mix design. And finally, we are now going into the product manufacture. It could just be straight ready-mix concrete, but it could be various cast products. It could be bridge beams, it could be just low-strength blocks, and then we might need thermal curing to increase the strength of those. In many cases, lower strength products like blocks and bricks and so on, which may only need to be 10 megapascals or less, can just have ambient curing. And then, of course, we dispatch to market once they've cured. These are a range of feedstock sources here. Just some case studies, really. We probably don't need to spend too much time talking about this, but 3 very different case studies from Western Australia that we've been working on for several years. We have the town of Collie on the top left there, where we generate a lot of our electricity by burning coal. We're still at about 50% electricity production from coal in Western Australia, about 20% are renewables, and that's going up quickly, and probably 20 or 30% gas. But probably fairly soon the renewables will be up around 50%, and the goal is in the coming years to have renewables as a much larger portion, and the coal power stations will stop probably around 2030, and then the fresh fly ash will dry up thereafter. But in that particular mix design for that first case there of Collie, we mix the residue from bauxite refining, we call it red mud, and then we add the activated chemicals and go into concrete batching. If we go to somewhere like Kwinana, which is a large industrial area in Western Australia, that has a large lithium industry there. So the DBS is delithiated beta spodumene. That's an industrial byproduct of refining the lithium. And you could in fact mix that with construction demolition waste, and then add the activated chemicals and use local batching to produce a range of products from that. We can go to the far north of Western Australia, and we can use the iron ore tailings from the iron ore industry there, and we can use metakaolin derived from kaolin clay in the overburden. Actually, this is something I'm interested in for Sri Lanka as well, because I understand that there are some kaolin deposits there, which is used for the ceramics industry, and so we can convert the kaolin into metakaolin at about half the temperature that you normally use for Portland cement, and so 750 degrees instead of 1500 degrees, and that we can make a geopolymer in Sri Lanka from either the fly ash from the coal power station or with the metakaolin, and then for aggregates we could use C&D waste if we wanted to avoid the use of virgin sands and aggregates. But interestingly, in Sri Lanka, Indonesia and China, where I'm working, we can use rice husk ash to make the sodium silicate. So there's interesting opportunities in all of these different places. Now, getting back to Murdoch University, we started the research in 2020, and that's when we established our lab. And you can see some of our research team there, and this photo is of Greg Blasiak. He's continuing with his PhD now, and he completed, first of all, his engineering honours thesis. He's standing next to the compressive strength machine there, and he's got some of those blue cylinders ready to cure those samples, those cylinders, and when they're cured, we'll put them in this machine and test the compressive strength. And you can see his paper there on Geopolymer that you can download there from his honours research. Now, we have another PhD student in our team at the moment, Ugyen Laki from Bhutan, and she's been particularly focused on using recycled aggregates for low carbon concrete, and her work has shown that these are more than sufficient in road construction, for example, and we can use them in geopolymer concrete as well, and achieve the same results under the standards as you would for normal virgin sands and aggregates. So we have very large stockpiles of this demolition and construction wastes, and so if we can harness these by following the principles developed by Ugyen in her research, then we can have enormous environmental benefits by having done this. And you can see Ugyen here in the bottom photograph. in our mineralogy lab, and she's just showing some of our master students the various sieving techniques and screening necessary to get the particle size distribution worked out from these aggregates. If we look at some of the other research that's occurred in Western Australia by Professor Van Riesen, he produced with his PhD students some very useful papers on how we can develop a procedure for having the mix design for geopolymers using X-ray fluorescence machine and X-ray diffraction machine. And so this gives us the data that we need in order to prepare the mix design for a geopolymer. And luckily at Murdoch University, we also have a very good XRD machine, a Rigaku unit from Japan. And there's Dr. Hans Oskieski, who's in charge of that machine, and we're able to use that to do some of our mix design work for preparing these geopolymers. So we do that by determining the bulk composition, firstly with X-ray fluorescence, and then the amorphous composition of the reactive aluminosilicates is determined by using this quantitative XRD method. And then we can also use scanning electron microscope there, point number 3, to reveal the formation and texture of amorphous to semi-crystalline geopolymer gel that binds the material, the degree of geopolymerization, and the resulting mechanical properties that we get after we've prepared the mix design and done the cast, and then we want to start testing it. So again, on mix designing, there was some interesting work done in the UK as well by a team of people there that they wanted to develop a particular, straightforward method for using calcined clays, metakaolins, as well as other industrial waste like granulated blast furnace slag. And they used a range of techniques like geological survey maps, XRD, thermogravimetric analysis, and compressive strength testing to and put together a set of standardized practices like a screening test, and that's shown there in that flow chart. And that became a particularly useful structured method to do that. And they show the results in their paper there. Now, what's interesting in Western Australia is that we have a growing lithium industry. So we mine the spodumene ore in Western Australia at several locations. And then so far we have 3 lithium refineries. And these refineries produce lithium hydroxide, which is exported to typically China, where that's turned into batteries for all of our phones and electric vehicles and so on. But that's only about 10% of the ore that actually ends up as lithium hydroxide. About 90% of it is actually a residue, which is called delithiated beta spodumene. And this residue, it turns out, is very much like fly ash from a coal-fired power station in that it has a high proportion of reactive amorphous aluminosilicates, and that can serve as an excellent precursor for geopolymer concrete. But again, getting the mix design right is quite tricky using those various test methods that I mentioned. And only now are we starting to learn how to do a fairly reliable mix design. And this, as I'll mention shortly, is under commercial production trials at the moment. But this particular research in this paper here was done by Professor Ali Karek at the University of Western Australia. And he's written a number of papers actually on using the lithium residues. He was particularly focused on mix designs with blast furnace slag from steel mills. But of course, in Western Australia, we don't have a steel mill. So I was particularly interested in finding new mix designs that did not rely on adding any blast furnace slag. And so we are now relying more on mixes with fly ash and kaolin, and without any blast furnace slag at all. And so this is just showing this chart here that Ali Karek has done is just showing the typical XRD analysis spikes that you're looking for in the geopolymer product, and the SEM analysis that you look for in the both the precursor materials and also in the product afterwards. And this scanning electron microscope allows us to study the geopolymer morphology, the microscopic structure, and understand its macroscopic behavior. So that was really useful work by Professor Ali Karek. Now, what we're starting to move into now at Murdoch University, and you can see here, Greg, in the photograph, is the use of other test methods as well, like this machine you can see in the photograph, the Fourier transform infrared spectroscopy. And this is looking at the functional groups and the chemical bonds present in the geopolymer. And from this FTIR scanning, we can see the dissolution rates that indicate the level of reactivity. And what we've learned is that the FTIR is more sensitive to the amorphous phases than the XRD. But what's been really interesting is a new approach that we're testing at the moment, and that is the co-calcination of different industrial waste. So, of course, the clays like kaolin, they do need to be calcined from kaolin to metakaolin, so that we can shift them from the crystalline phase into the amorphous phase, and they can become a reactive precursor. But what we're now looking at, following the advice in this paper by Professor Pays and Hertel in Belgium, who for many years have been working with the bauxite refining residues, what they found is this very useful technique of co-calcining the kaolin with bauxite residue. And this can produce a very high quality supplementary cementitious material. And so in the photograph there, that's in our pyrometallurgy lab at Murdoch University, and we're just showing some of our master's students how to do this calcination procedure at 750 degrees Celsius. And so what we found is that we can actually co-calcine this red mud and kaolin at 750 degrees C, and it can be used as an SCM or a geopolymer thereafter. And the great thing is that because the challenge of using industrial waste materials, and if you use that in public infrastructure, you do run the risk of leaching heavy metals and other substances, contaminants, pollutants into the environment. So we have to do then leaching tests under particular well-defined standards to determine the extent of this risk. And what this co-calcination method has shown is that it decreases the leaching of particular heavy metals like chromium from the geopolymer mortars, and we were able to keep the concrete within the inert waste leaching limits as a result. So this is what we're actually working on now with similar materials in Western Australia to what Pays used in Belgium, and we think it holds great promise for the future for recycling these more difficult industrial wastes. And so what it finds is that typically an optimum co-calcining percentage is around 20%. So this is the mix designs that we're working on at the moment, and we'll take these into production with those companies in the near future. So this is where we're at the moment. This is the final phase and most complex phase of understanding this leaching of heavy metals and other substances from the cast geopolymer concretes. And so there's a particularly useful European standard, but a number of countries have their own standards that are used, and there's a number of papers now that have conducted these tests with industrial waste going into geopolymer. In this example here from China, and they're looking at the very same mineral processing residues that we're interested in Australia, which are nickel slag, lithium slag, and metakaolin. And these are of great interest in Indonesia as well, where we're also working. And this is just their graphical summary abstract, showing the steps that they've gone through to look at these different geopolymers and their leaching characteristics, and to learn how this immobilization of heavy metals actually occurs. And so we had in fact started some of this work in our own lab in a very rudimentary manner with Franklin. You can see there in the photograph when he first started working on the red mud residue from the bauxite refineries that we have in Western Australia. And he had actually started that basic leaching work, and now Greg is actually taking this into a more advanced level, and we hope to start commercial production trials with these residues in the near future as a result of that work that Greg's doing now. So all of this now is on a journey to commercialization because we have an IP investment partner, a company that is now called Green 360 Technologies, and formerly known as Suvo Minerals, and they're a kaolin miner from Victoria, and now they've had an IP agreement with Murdoch University and formed a joint venture partnership with the largest precast concrete company in the state, which is Permacast, and we're now in commercial production trials on some of these mixed designs. But just to reflect on the history so far, 2020 was when we first started our geopolymer lab at Murdoch University in a very simple way, and little did we know that it was going to be so complex to actually get to this point. And in 2021, we started some very basic field trials in Collie, which is where the fly ash is generated from the coal-fired power stations. And basic field trials there in the concrete batching plant. And then we actually went into the Muja coal-fired power station in Collie, probably the biggest coal-fired power station that we have in Western Australia, and in one of the empty warehouses we actually started manufacturing wall panels with geopolymer that we made at the batching plant in geopolymer, and that actually was able to work effectively. We did have an unsuccessful field trial later in 2024, trying to get ready mix to work. That was also quite difficult, and so we've gone back to the drawing board in 2024, and I think we're in a much better place now with the mixed designs that Greg's working with at Permacast, and that's where we're up to there now in 2025, that last photograph. So you can see there Greg at work in one of the big warehouses at the Permacast concrete factory, and we're now trialing a number of different mixed designs, including the fly ash, the kaolin, the red mud, the dilithiated beta-spodumene, and we have a number of these underway now, and very soon we should be able to ramp up into commercial scale production with those geopolymer concretes. And the thing that people are waiting on from us now are the actual data sheets, but we can only complete these now as we go into this final phase of testing using those leach methods to make sure that we're not leaching any contaminants like heavy metals into the environment. So one of the other pieces of work that we're doing, as I mentioned earlier, is Amitha's work on the database developments. And so the aim there is to support sustainable initiatives in various countries and, in order to produce this concrete from mining residues. And so the database will store detailed information on these residues, like their location, chemical composition, the volume, and the environmental conditions. And to develop that fully, we want to make use of geospatial tools and stakeholder engagement. And we will be looking at various case studies at sites in Western Australia, Indonesia, and Sri Lanka too, we hope. Okay, so and the features there will store and retrieve mine tailings data, identify crucial data points, determine suitable wastes for the geopolymer production. We'll locate suitable sites based on mapping, analysing data to create interactive reports and dashboards, and transform. Well, I should go now to the conclusions. And so particularly with that database, what we're hoping to do is transform agricultural, mining and construction residues into low carbon concrete with a particular idea to address two chief challenges: carbon emissions and industrial waste management. And so we want to improve the efficiency and sustainability of tailings management and resource efficiency, and reduce the environmental impacts of this waste storage. And this could enable low carbon eco-concrete for sustainable developments. And this would contribute to the creation of a circular economy. And so in particular, this interactive database will assist the transition to a sustainable construction industry, and the database will help map and enable the identification of alternative materials and local sourcing. So thanks very much, everyone. That was a quick run through and summary of the work that we're doing at Murdoch University in the geopolymer concrete space. So I guess, Mrs. Chinta, I should stop there and take any questions.
Yes, thank you so much. It's very inspiring speech, actually, the presentation on industrial waste to low carbon geopolymer concrete. I think it is a kind of sustainable material what we need in future for sustainability of our in the industry, that construction industry. It is very important. Even now the presentation is open for questions. And one question is there.
How does the use of industrial byproducts such as fly ash and slag in low carbon geopolymer concrete affect its mechanical properties and long-term durability compared to conventional Portland cement? Yes, well, fly ash and slag are the classic precursor materials that have often been used historically in a number of parts of the world to make geopolymer. And these materials, fly ash and slag in particular, have been shown to be amongst the most effective precursor materials and can achieve the same levels of mechanical properties and durability that you will get from conventional Portland cement. So yes, the answer is that yes, particularly those two industrial waste, fly ash and slag, can actually achieve similar properties to normal concrete. That is the answer to that question.
Yes, thank you so much. Another question is there thank you very much, Professor. And I would like to ask questions about properties of geopolymer concrete. How does its durability compare to traditional materials?
How does it, which one's this? How does its durability compare to traditional concrete? Is that the question? Yeah, look, well, that's it. It's all in the mix design. It's all in the waste characterization. If you're able to achieve the right mix design, which results from the characterization step 2 that I mentioned earlier, we can achieve an equivalent concrete to normal Portland cement concrete. This is what all the research has shown. But this is the thing. There have been thousands of papers written all over the world on geopolymer, and professors have achieved very successful geopolymers in the lab in many locations around the world, but we don't see a lot of commercialization of it. And that is because scaling up from the lab to the field is a very different question. And what we're dealing with, the main challenge is these industrial wastes are highly variable in nature. Whereas after 200 years of Portland cement, we have been able to achieve all over the world a very stable and reliable product that works incredibly well. So to come along and try to replace that with industrial waste materials, which are highly variable, is a big challenge. And new methods have to be developed, and it can become quite easy to do this in the laboratory, where we have very strict controls over the laboratory procedures and the input materials and so on. But once we go to large scale with a range of sources of the materials, we have to develop new methods to have good control over these feedstock materials, because we have to manage the ratios of the alumina silicates with the chemicals very carefully. So I hope that answers that question. And yes, I'm very happy to share the slides as well, Mrs. Chinta. Someone had asked for the slides, so there's no problem.
Yes, thank you so much. And someone want to ask a live question, so?
Is that?
Yes, another from our Dean, Faculty of Agriculture, Professor Jayasinghe.
Yep.
He asked many questions. You can see, no?
I can see them, yes. How about the availability of uniform raw materials? It is a significant challenge. And one piece of research we're starting is can we do advanced analytics as the feedstock materials, the raw materials are entering the process. This is something that we're very interested in trying to understand if we can have a dynamic monitoring system of the feedstock materials, because they may be constantly changing, those feedstock materials, and we have to be able to manage that. Curing, geopolymer responds well to curing. Obviously, that's going to take more energy, and what we're always conscious of is what is the most energy efficient way of producing these precast products in particular. If we can reduce the amount of thermal curing necessary, well, then we reduce the energy inputs, which is important to reduce the carbon footprint. Eventually, of course, we'll transition to renewable energy, and perhaps in the future, once we've sunk the capital into the renewable energy infrastructure, thermal curing may not be such a problem. Workability is always an issue, because the geopolymer is more viscous than normal Portland cement concrete. So we have to manage that with maybe a super plasticizer, different mix designs to get the workability right. That's definitely a challenge. The cost, we have to always be mindful of, and the biggest problem that causes the cost management issue are the activated chemicals. These can be expensive to get good quality, and so in the longer term, we probably need to look at how can these be made on site, also with waste materials. And so this is something we're looking at as well. Shrinkage and cracking. Yeah, this is definitely something that has to be managed as well. And this is why the production trials are important. And we're doing the various thermal testing to check for this shrinkage and cracking, and this is part of the current program. And the share in the world economy, well, it's probably less than 1%, I would estimate, but it's hard to know. But we do have a very successful company in Queensland in Australia called it's Wagner's. Wagner's. We have a company in Queensland that has been making geopolymer concrete for some time now. They're mainly using fly ash and slag as the primary feedstock material, the primary precursors. And they have a website, Wagner's Concrete, and they have their geopolymer product is called EFC, Earth Friendly Concrete. So, and in fact, they have a separate website called EFC, Earth Friendly Concrete. So that's a good example of a successful company in the world. So I hope I answered that very good list of questions there, Dean.
Yes, and Ms. Niranjala, you are interested on asking questions. By unmuting, you can ask questions.
Hello, am I audible to you all?
Yes, yes.
Yes, okay. Thank you very much for the very informative presentation, Professor. So I'm very much interesting about this sector because recently I'm working with like ferrochromium slag, waste slag, and recently we have come up with some concrete, and we have used different mixed ratios, and we come up with some series of concrete blocks. So I just want to know, you mentioned about this to measure the environmental impacts. You are doing these leaching tests.
Yes.
So yeah, so we also planning to do this leaching test, and also I would like to, and our team would like to do some toxicological tests. So what we want is, we just want to extract. So for the toxicological test, we need some like solutions, extracts. So do you have any idea about like how we can get these extractions? Because usually when we are doing like toxicological test, we use some organic dilutes and mainly sometimes distilled water, and for this ecotoxicological test. So Professor, do you have any idea about that, how we can make these extracts for our further assessments?
Yeah, look, this is the phase that we're in right now. So we are learning from the publications that I shared with you in my slides. And so if you'd like to keep in touch with me in the email, we can definitely share our experiences with you as we go. We will be soon preparing a paper on this, so we document all the methods. So please keep in touch, and I will happily share this information with you.
Thank you very much, Professor. Of course, yes, I will send an email to you. Thank you very
good.
much.
Yes.
And yes, another question is there in the chat box. What are the environmental benefits and potential trade-off associated with the production and use of low-carbon geopolymer concrete compared to traditional Portland cement concrete?
Well, I guess we touched on this throughout the presentation. The key environmental benefits that we're seeking is a reduced carbon footprint, because as you may remember, at the beginning of the presentation, I said that Portland cement is the world's single largest source of carbon emissions, and we're now on the goal to stop these carbon emissions. So if we can find alternatives like geopolymer, then we have the benefit of reducing carbon emissions if we can do this properly. the other benefits are that if we're able to use these industrial waste materials, well, then we provide a good solution to what could otherwise be an environmental impact. So the trade-offs, well, the trade-offs are, as we go into any new industry, is a big capital investment to set up the new equipment that we'll need. We will have a high carbon footprint initially of the activated chemicals. So the challenge is to keep that proportion as low as possible so that we don't, in fact, end up with a higher carbon footprint. As some people have found in their research, you could actually end up with a higher carbon footprint than ordinary concrete if you don't manage the activated chemicals properly in the mix designing. And the workability of the geopolymer, because of its higher viscosity, is a challenge. So yeah, there are some trade-offs, and over time, we need to learn how to manage these. So of course, Portland cement has had 200 years, and geopolymer has only had, 1 or 2 decades so far, and it's not even fully commercialized yet. So we've got a long way to go, but we're very hopeful and confident. Thank you.
Thank you so much. Then I think as the last question, maybe, may I ask about, because Sri Lanka is an agriculture country, because our rice production is around 2 to 5 million metric tons per year. Then out of that, around 20% rice husk. What are the challenges if you are using get the silicate from rice husk for geopolymers?
Yeah, look, the challenge could be is that in some cases, farmers may want to return the ash to the soil to ensure that silica is returned to enable the strong growth of the rice stems themselves. Which is where the silica is needed. But on the other hand, challenge then is finding an economically viable way. There's like Sri Lanka is a source of a lot of rice, and see if we can develop a project in that way. And again, once we get success in the lab, we will then need a commercial partner, an investor, to see if we can actually go into commercial production trials for that.
Thank you so much. I think we get many information from about geopolymers, because for our construction industry, we know that Portland cement production is huge emissions, carbon dioxide emission, environmental issues. There are many, and therefore it's a very good solution for the sustainable solution for the construction industry. Thank you so much. You are valuable. You shared with us very valuable information today, especially in our Sri Lankan community. Thank you so much. And I hand over the mic to the Dr. Dushan to end up the session. Thank you so much.
Thank you very much, Madam Chinta. On behalf of the ISA 2025 Organizing Committee, I would like to extend our heartfelt gratitude to Professor Martin Enda for sharing his valuable insights on low-carbon geopolymer concrete. We truly appreciate your time and experience, sir. Thank you very much, Professor Martin Enda. A special thank to Ms. Chinta Rupasinghe for moderating today's session. Your contribution was invaluable in making this event a success. To all our participants, thank you very much for joining us. We hope this session was insightful and beneficial. Big thank to also to the everyone who worked behind the scenes to ensure a smooth event. Before we conclude, quick reminders. So e-certificates will be issued via the Lanka Education and Research Network through the Micro Rewards platform. Once ready, you will receive an email at the address provided during the registration process. So recording of this webinar and all the previous webinars are available at the ISAE official website. So we encourage you to view and download them. Our next pre-symposium seminar is scheduled for 9th June at 7 p.m. So the ISAE 2025 will be held on 2nd of September at the Golf Face Hotel Colombo. Registration is now open, and we are looking forward for seeing you all at the conference venue. We encourage you to stay connected with us through our website and social media platforms for update and more details. Once again, thank you very much and we look forward meeting you again in this kind of webinar series. Have a wonderful evening. Thank you very much.
Thank you so much.